Okay, so unfortunately yesterday the slides did not record as they were supposed to. So I'm doing this new recording from my office. So this is a lecture on software visualization. The first part will be on visualization design, and the second part will be using the principles of visualization design to explain some various software visualization techniques. So I'm Marius, and I'm a PhD candidate at the University of Oslo. I have a master's degree in visualization, and currently I'm researching visualization of technical debt. So what is visualization? To create a visualization basically means to create a visual representation of data. So you are mapping data to graphics. There are two main areas of visualization. One is mainly concerned with spatial visualization or three-dimensional visualization. And the other one is mainly concerned with multi-dimensional visualization and mapping multiple dimensions onto a two-dimensional screen, right? So in the 3D space, first of all, we have volume visualization, concerned with visualization of scalar fields. And this is very important in medicine and biology and geoscience and engineering and more. Very often it's about MRI data and CT scans and other types of medical data, as you can see in these examples. Flow visualization is also in the 3D space. So here we are visualizing vector fields, which are basically arrows in 3D, discretely placed in 3D. And each arrow says something about the strength and direction of flow at some given point in time. And this data is typically from simulations, but it can also be recorded from reality. Information visualization. So this is in the multi-dimensional space. And this is software visualization is in this space. And here we are concerned with high dimensional data and hierarchical data and textual data and more. And there are many different techniques here. Visual analytics is adding a computational component to information visualization. So maybe you are visualizing the data before the computation and after the computation. And maybe you are also visualizing the computation itself. So you're checking to see if your computation is done correctly. So why do we even want to visualize? Well, first of all, our visual system has evolved over millions of years to detect patterns and anomalies quickly. So for instance, looking at this map, I can spot anomalies very quickly. So there's a lot of red in the middle, and there are these blue islands, and I can spot them very quickly. Here's a blue island in like a sea of red. Here's another blue island. Here's one more, and here's a red island in like surrounded by a lot of blue, right? So it's quick to spot these outliers, right? And also I can get an idea of a pattern here. So along the coastlines there's a lot of blue, so along the edges of this map. And I would assume this has something to do with big cities, because big cities are usually located along the coast. So I can get some ideas about this, about why I can see all this blue here and why there's so much red here, right? And why these outliers are here. And we are also leveraging this high bandwidth. So if you wanted to explain this map using text and numbers, you would need a high amount of it. It would be many pages, right? But now I can compress all this information into these visual channels instead. So I can fit a lot of information into a small image. So when you combine these two, visualization accelerates knowledge gain. You don't need to read through all this text and numbers, and you can spot patterns and anomalies very quickly. So here's an example. How many times does the letter V occur in this string? So it's hard to count it like this. If I do this, it's suddenly much easier. So I can count 4 V's, but I can also get some ideas about some pattern. For instance, I can see there's 1 V in each line, and the V's seem to occur a bit earlier in each line, not in the last part, but in the early part of each line. So if I would add a new line here, I would expect 1 V, and probably it would end up somewhere around here. So I can make predictions based on what I'm seeing. Another example, which of these 50 numbers occur most often? So it's pretty hard to start counting it like this. You have to keep all the numbers in your head. But if I do this instead, show it like this, we can quickly spot the most occurring number, which will be 60. And I can also spot the second most occurring numbers. And I can also spot the numbers that don't occur at all, like 100 and 80 and 40 and 20 and 0. And I can also get some ideas about patterns, right? Or distributional patterns. So, for instance, I would say maybe there's some distribution happening around 60 and another distribution happening around 20. So you can make some ideas, right? Some alternatives to visualization. First of all, AI methods. So you could give this list to ChatGPT and ask it this question: which of these 50 numbers occur the most often? And it might be able to give you a pretty good response. It might be able to actually find 60 as the most occurring number. But it might also not, right? So ChatGPT is not known for its counting abilities. So it might give you a good answer, but it might not. And also, every time you ask it, it will give you a new answer. So it can be inaccurate, but also hard to control the output. Another thing you could do is statistical analysis. For instance, descriptive statistics, but this will abstract the data and remove details. So, as an example, this is Anscomp's quartet. It's very famous. So Anscomp defined 4 different data sets. So these are 4 different data sets here. And they all have the same mean of x and y, the same variance of x and y, the same correlation between x and y, and the same linear regression line. But when you plot each of these 4 data sets like this, you can instantly see they are very different. So statistically, these are the same data set, but when you look at it, so for instance, the first one here, right? It looks like a linearly increasing phenomenon. The points are varying around the line somewhat. So maybe this is some natural phenomenon you're recording, and this is some naturally occurring noise. It could also be because there is some noise in your measurement device. If I added a new point at x equals 16, I would expect it to end up somewhere around here. So the regression line is a pretty accurate abstraction of this linear phenomenon. Right. Looking at this second data set, we can see that the line doesn't fit at all. So this looks more like a polynomial type of phenomenon. So if I would add a new point at x equals 16 here, I would expect it to end up here, not up here. So here it will be more correct to use a polynomial regression line instead. In the third data set here, we can see that the regression line is almost correct. And so we can see that this is something that looks like a perfectly linear phenomenon. But there's this one outlier that offsets the regression line. So this outlier here, it could be an error. Maybe you made some mistake while measuring, or it could mean there's some phenomenon around x equaling 12.5 here that makes y rise. So this might even be what you are trying to capture. But it could also be a mistake. So the linear regression line doesn't really fit here. Yes, and then in this fourth version, or fourth data set here, we have many points that are all on x equal 8, but y is varying. And then there's this one outlier. And this could be, of course, like here in the previous one, it could be a mistake, but it could also be something that happens with x when y equals 12, right? So if y is 12, x rises. So you get much more information by plotting it like this, but you can use the descriptive statistics in addition, so you get both. So I hope that was a good justification for using visualization. And now I will be talking about how to design your visualization. And I'm using Tamara Munzner's framework. So she defines visualization in this way. Computer-based visualization systems provide visual representations of datasets designed to help people carry out tasks more effectively. So you have these visual representations of data, but you also have this carry out tasks more effectively. So there's an interactive component as well, which is equally important. So the way she describes her design, or she has a framework called problem-driven visualization design. And the way she describes it is using this nested model. In this nested model, on the top, we have this domain problem characterization. So when you want to design your visualization, you start with the domain problem characterization. So you want to define who are the target users and what do they need. So you have to figure out who the target users of your visualization are. And if you might be the target user yourself, and then you might have some ideas about what you need in your visualization. But you might also not be the target user. Then you need to go and talk to the target users and try to understand what they need from your visualization. And understand the problem they are trying to solve. And when you understand the problem that they are trying to solve, I've written it down. You can do this data and task abstraction. So that would be your next step. And in this step, you try to translate from the domain problem characterization to a visualization vocabulary. So you take the domain problem characterization that you made, and then you try to understand what you need to show. So that would be the data abstraction, and why the user is looking at it. That will be the task abstraction. And I will show you this after this slide. Once you have done this data and task abstraction, it will be much easier for you to do the visual, or to find the encoding and interaction techniques that fits your data and task abstraction. So this is concerned with how to show the data, right? So you're looking at how to draw it, but also how to manipulate the drawing. Then, of course, in the end, you need to you have to create the algorithm. You have to program it. And so in the end, you find the algorithm of how to actually map your data onto graphics in this way that you have described, right? So starting with data abstraction. So let's say you have done your domain problem characterization. Now you need to figure out what you need, what data you need for your visualization. So in the data abstraction part, we need to first of all figure out the data types. So this would be items and attributes. The items are what you need to measure, and the attributes are the measurements on those items. You have some different types of data sets. So in software visualization, we mainly use tables, networks, and trees. And trees are a subset of networks. So basically, we have tables and networks, right? There are different types of attributes. We have categorical, we have ordinal, and we have quantitative attributes. And these can have different ordering directions. They can be sequential or they can be diverging. So an item has attributes. So the item is this thing that you are measuring, and it has attributes. And there are different types of attributes, and these have different ordering directions. So, for instance, a table. A table is that's a data set type, and a table has items as rows, and the attributes will be the columns. So, for instance, in this example, we have items, this will be observations. So we have 21 observations there, and each observation has some attributes. So here, for instance, we have a categorical attribute, town, and we have some, this will be diverging quantitative attributes, longitude and latitude. And there are some others as well, right? So for each item, there's a unique set of attributes that was measured. So you have items as rows and attributes as columns, and then an item attribute pair would be called a cell. So that will be one value in the table. We also have the network type, dataset type, and in this dataset we have nodes, so these will be the items. But in a network we also have links between the items, so this would be between the nodes, and this would represent some relational quality. So all the items have some relationship. And this relationship can have its own attributes that you could measure. And this is often called a weight. So, but importantly, the nodes are the items, and these items have attributes, but we also have these links, right, which also can have its own attributes. A tree is a subset of a network. It's a special kind of network. And the trees, in trees we have two types of nodes. We have the leaf node and we have the branch node. And the link is usually representing some hierarchical relationship. So it's still a relationship, but it's hierarchical. So for instance, these two leaves belong under this branch. So they are part of this hierarchy. And these two belong under this branch. But these both of these belong under this root node, right? So these are, so the leaf is an item that can have attributes. The branch is a different type of item that also can have attributes. And then the link can also have its own attributes. So we have sort of three different types of items here. Okay. So when you have done the domain problem characterization, you also want, and you have done your data abstraction, you want to do the task abstraction. And here you are mapping your domain problem characterization onto visualization specific tasks. And this is done using what's called action target pairs. So Tamara Munzner has defined this table of action target pairs, and these define your core visualization tasks, and these cover probably 90% of any task you will need to describe, visualization specific task. So the way this works is you pick one action from this side, and then you pick a target from this side. So for instance, you could say you would like to discover outliers, or you might want to compare features, or you might want to present trends, or summarize distributions, compare topology, identify paths, and so on, right? And if you do this, task abstraction, this next part here will be much, much easier for you to do. So based on your data and task abstraction, you start to define how to actually draw the visualization. This is a very big topic. This is the main topic of visualization. It's too big to cover in this short introduction. So I will be focusing on a small part of it. So mainly this part of encoding. But if you're interested in learning more, you can get this book by Tamara Munzner. So it explains all of this. So when you have your items, you have a data set of items. You need to figure out how to draw them, right? So marks represents these items, or links if it's a network type dataset. And then you have the channels, which controls the appearance of these marks. And the channels will express the attributes. So marks can be points or lines or areas. And then the channels can be how you color them, or which shape you use, or maybe the size of them, right? And these channels have been ranked by their effectiveness. And this is based on empirical research. So there has been numerous studies on this. And based on those studies, they have made this list of the effectiveness of these different types of channels. So we have the ordered or the magnitude channels, which you use on ordered and quantitative attributes. And then we have the identity channels, which are used for categorical attributes. And so when you are creating your visualization, you should start on the top here. And as you sort of spend your channels, you pick something further down. So you try to use the best channels for the most important attributes. So as an example, let's say you have this data set of 3 items with 5 attributes each. Maybe you want to visualize one attribute in each item, one quantitative attribute. Well, you can use a bar chart. So in a bar chart, the mark would be a line and the channel would be vertical position on a common scale. So this is the most effective channel. And so this is a very popular type of visualization and very effective. But maybe you want to show 2 attributes. Well, you can still use position on a common scale if you make your items a point instead. So the mark now is a point. And now you can use the vertical and horizontal position. And this is called a scatter plot. Maybe you have a third attribute, a categorical attribute that you want to visualize. Well, now you can use a color hue on each of these points. So now you're showing 3 channels. Maybe you have a 4th attribute that you want to show. And now we have spent our position on a common scale. And let's say this is a quantitative attribute and you have spent your position on a common scale. Well, you could pick size, for instance. So now the size of the points show this 4th attribute. And now this small visualization here is showing 3 times 4, 12 different values. A very popular type of visualization is the bar chart. And the bar chart uses lines as marks, and position on a common scale would be the channel. But you can also use coloring and groupings in some different ways to express categorical attributes. So I'm not going to go into too much detail on this here, but I can recommend this paper if you're interested in this. It's a one-page paper, so it's quick to read. It's very informative. Box plots use lines and points as marks, and they combine these marks, multiple of them, and they all utilize position on a common scale in a very effective way. So a box plot is a visualization of a distribution. And we have some distributions here. And here we have the box plots that are representing these distributions. So let's take the normal distribution here as an example. So the bar, this red bar, is showing the interquartile range of this normal distribution. Then there's this vertical line that is showing the median or mean value of this distribution. We also have these whiskers that show the minimum and maximum values of this distribution. And we have these dots that show the outliers. So these are all multiple marks that exploit the same channel, right? Position on a common scale, but they have been juxtaposed on top of each other in this very clever way. So it's a very effective type of visualization, very effective technique. Line charts also uses points and lines. So let's say you have a cat and you want to weigh it to keep track of its weight, and you weigh it once a year, and you plot your result into a chart like this. So what you can do if you do that is you can add a line between each point. And this line will represent a continuous relationship between sample points. So let's say for instance, you have weighed it in 2004 and in 2005. Now, when you have added a line, you can actually say the weight of the cat halfway between 2004 and 2005 by looking at the line. Also, this line expresses the velocity of change during that period. So here we can see that the change in weight was slowly increasing, and then at some point here between 2008 and 2009 there was a very rapid increase in weight, and then it stopped, and then there was a rapid decrease in weight. So you can look at the angle of the line and to understand the velocity of change during that period. So they are representing a continuous relationship. So when using line charts, both attributes should be continuous. If one of the attributes is categorical, you probably want a bar chart. So I found this example on Google where they have these categorical attributes, state names, and one continuous here, quantitative, which is millions of dollars in income per state. And so here they have marked the income for each state, but they have drawn this line between each state as well. But this doesn't really make sense because states are not a continuous relationship. You can't be 0.1 Illinois and 0.9 Indiana, right? So you're either this state or this state. So this is probably wrong. So in this case, you should use a bar chart instead. Scatter plots use points as marks, and the channels will be horizontal and vertical position on a common scale. But you can also use the points size and color and shape and so on to express other attributes. And so this is a very effective style of visualization because you can add many channels to it. And it's useful for a broad range of cases. So here, for instance, we are using the size and the coloring and also, of course, the positions. Networks can be expressed in using many different techniques. One of the most popular techniques is the node link diagram. And in this technique, the nodes represents the items. So they are drawn using a point mark. And links represents relationships between the items, and these are drawn using line marks. And the channels, so both the nodes and the links can use separate types of channels to express some attributes. So, for instance, in this example, the nodes are using color and size to express some attributes. And the links are using thickness and color to express some relational attributes. So this could, for instance, be the weights, right, of the links. It's usually called weights in networks. Networks can also be drawn as matrices. This is called an adjacency matrix. And here the nodes, so the items, are represented as rows and columns of a matrix. And the links are represented as cells in this matrix. So for instance, if we take a node link diagram here and express it as a matrix, we can see that, so we have these 5 nodes, and these are, so 0, 1, 2, 3, and 4. These are drawn as rows and columns instead. And the links, so let's take this link as an example between 1 and 2. Here you would put it as a value in this matrix instead. And so these matrices are very space efficient. So they are very useful for very large networks. So a node link diagram type of network very quickly becomes very noisy and complicated. And so matrix can be very helpful if that happens. And in this example here, so these cells represent the links, and they are using colors instead of numbers to express the attributes. So here are the different colors. So these are people, and the color of the link expresses some relationship between these people. So red is family member, green is co-worker, blue is enemy, and so on. trees are a tree is a type of network. So these can also be drawn using node link diagrams, where the nodes represents items and the links represents relationships. But here the links represent hierarchical relationships. So for instance, here these nodes would be your items, and the link, and so you have the branch nodes as well, and the links here. So these items are all hierarchically under the same branch, right? There are many different ways to lay out trees. So here, for instance, is a radial layout, which is very space efficient, but it's very difficult to lay out trees because of this combinatorially increasing complexity. So they become really big really fast. To alleviate this complexity, branches can be closed. And that is called an indentation tree, when you can close your branches. So here we have an example. And this type of tree is usually what you would see in your IDE, right? So you have, in this example, you have files and folders. The leaf nodes are representing one type of items. So that in this example, it would be files. And the branch nodes represent a different type of item. And in this example, it's folders. And in an indentation tree, the subnodes in an unopened branch are hidden. And here they are using some different channels, right? They are using color to express whether the folder is open or not. So these light blue nodes are open folders. These dark blue nodes are closed folders. And then these orange nodes are the files. Yeah. And so they are colored differently from the branch nodes so you can easily identify them. But you could use some more channels here to identify, for instance, different types of folders or different types of files. And in your IDE, they are usually using like an icon for each file type, right? So you can identify different types of files from each other. And trees can also be drawn using what is called a tree map. So in a tree map, leaf nodes are represented as areas, and the enclosure of these areas represents the hierarchical relationship. So here, for instance, in this example, we again have files and folders. And so each of these areas represent a file. And the size of the area represents the size of the file. So we can quickly spot the bigger files, and the smaller files would be the smaller areas. And then they are all enclosed in these enclosures, which represents the folder they are in, right? So that would be the hierarchical the branch. And so these are enclosed in this area, these files in this enclosure, these files in this enclosure, and these are all enclosed in this branch, and these are all enclosed in this bigger branch, and then of course you have the root node which encloses everything. So this is a very popular technique in software visualization because in addition to this, you can use more channels. For instance, you can use color, hue, and saturation, and so on, to express attributes of the files. So you can view many files at the same time, and you can view many attributes of the files also. 3D maps often use rectangles like this, but it's also possible to use other shapes. For instance, you can use circles, like in this circular tree map, or Voronoi tessellations, like in this Voronoi tree map. Okay, so that was the end of part 1. In the next part, I will be talking about I will be showing you some software visualization techniques, and I will be using the concepts from part 1 when talking about these techniques. Okay, thank you.